First, a very strong reminder to memorize your polyatomic ions. Memorize the name, the formula, and the charge of all of these ions. The ones that are in bold are more common than the others, but you should know them all. It's very important for the rest of your chemistry courses. Polyatomic ions are groups of atoms that are held together by covalent bonds, and they possess a net charge. When soluble ionic compounds dissolve, these polyatomic ions stay together as a group. Salts are another term for ionic compounds. We recognize ionic compounds because they contain a metal and a nonmetal, or a metal plus a polyatomic ion, or some combination of polyatomic ions. Salts can be soluble or insoluble, and we will learn solubility rules in order to predict solubility of ionic compounds. Calcium carbonate is an insoluble solid. If we add it to water, it will not dissolve. We stir it up really well, and the solution appears cloudy, indicating that the calcium carbonate is not dissolving. Over time, it'll eventually settle out. In contrast, sodium chloride is soluble. When we put it in water, it's going to dissolve and then dissociate into ions. The appearance of the solution is clear. Sodium chloride would be colorless, but there are other salts that when you dissolve can impart color to the solution. The important result is that when a soluble salt is added to water, it dissolves and the result is a clear solution. Sodium chloride, like any soluble salt, when it dissolves in water, is going to dissociate into ions. In the case of sodium chloride, we're going to see individual sodium ions and chloride ions within this solution. We're going to practice writing dissociation reactions. A couple points first. We're going to omit the phases for clarity purposes. S for solid, L for liquid, G for gas, AQ for aqueous or dissolved in water. We're going to omit these just so that we can focus on the important chemistry. As far as predicting charges for the ions, remember charges for the representative elements can be predicted using the octet rule. For the transition metals, you can determine the charge from context by remembering that overall the compound must be electrically neutral. The number of positive charges must equal the number of negative charges. So we're going to predict the ions that will exist in solution when these soluble salts dissolve in water. Bromine, 7A, 7 valence electrons, 1 electron short of an octet. It accepts an electron to go to a -1 charge. This subscript 2 tells us we have 2 of these bromide ions. The charge on copper has to offset the 2 bromide ions. So the copper ion is going to have a 2+ charge. Silver iodide. Iodide is another 7A element. It has 7 valence electrons. It's going to accept 1 electron to go to a -1 charge. Silver, therefore, it must have a +1 charge. Silver is one of the rare transition metals that always has the same charge. Silver is always going to be +1. Most of the transition metals can have more than one different possible charge. Potassium phosphate. We've memorized our polyatomic ions. So we know that one of the ions that's going to be present in the aqueous solution is the phosphate 3- ion. If we happen to forget what the charge on the phosphate is, we're in luck in this case, because we know that potassium, as a 1A metal, is always going to form a +1 charge. Potassium, 1 valence electron, it loses its 1 valence electron to go 1+. We see that there are 3 of these potassium ions, so the phosphate ion must possess a net -3 charge in order to offset the +3 from the 3 potassium ions. Next, we have another salt containing a polyatomic ion. In this case, it's the nitrate ion. We've memorized the nitrate ion as NO3-. The subscript 2 here tells us that we have 2 of those nitrate ions. Copper, again here, is going to be +2. We know we have to have a +2 charge to offset the 2 nitrate ions. Third example that has a polyatomic ion, in this case it's carbonate. CO3, 2-. Sodium, a 1A metal. It's always going to have a +1 charge. This 2 indicates that we have 2 of these sodium ions. So we've just practiced a handful of these dissociation reactions. You need to be able to do this because very often this is the starting point of more complicated chemistry problems.